So good morning, and thanks a lot, Thomas, for the introduction. So as Thomas just mentioned, my name is Eduardo Miguel from Ikerlan, and I am here since I am the coordinator of the Liberty project, one of the projects in the cluster. And I will share my screen with you in order to, just a second. Okay, I hope that you can see now my screen. So again, thanks, Thomas, for the introduction. Thank you all for being here, for taking the time to attend this webinar, and I hope that it's going to be interesting for you and also useful. So in the first stage, I will go through a very brief introduction of the COLLABAT cluster in general, as well as what we are going to see today, which are these 4 presentations that you can see on screen. After that, we will go for a panel discussion with the speakers we have here, and after that, a Q&A session with you all guys. So please be proactive, send us the questions you have, and we will address them as good as possible. I will introduce in the following the speakers, but just an important highlight for them. So thank you also for being here and for presenting us today your developments. So regarding, let me see if I can, there I go. So regarding the COLLABAT cluster, first of all, I would like to somehow illustrate in which points of the value chain our developments and our topics are located. So we will range from battery pack manufacturing on to the use of those batteries, going through the vehicle integration. So that's where we are going to focus the main developments that we have. And after that, we will go a little bit farther in the value chain to repurposing, remanufacturing, and recycling of those batteries that we are generating. So that's more or less where we are going to find the contents coming from the COLLABAT. So to give you a little bit more information, the COLLABAT cluster was created by the 4 projects that were granted into the LC button call. So most of us have, or all of us have, common objectives. To some point, they are slightly changed, but you will see quite a lot of common points in between the 4 projects, and the reason why is that we all come from the same EU-granted call. In that call, the general objectives is to accelerate the mass market take-up of electric vehicles, whether it is full electric vehicles or plug-in electric vehicles. We are going to be trying to do that by means of increasing the energy density of those battery packs and shortening the charging times, of course, by means of high power charging. If we get a bit more into detail, and the specific objectives that we are going to be tackling, all of the 4 projects, is to reduce the battery system weight. The call states 20%, that might vary a little bit from project to project. After that, extending the useful life of the battery packs at a minimum of 300,000 kilometers in real driving. Minimum again, and that changes a little bit from project to project, 20% life cycle analysis improvement comparing to benchmark products. And after, we are also facing an improvement in knowledge on module and pack sensorization, as well as thermal management. So that being said, and this being the common playground for the 4 projects, I would like to briefly introduce you each of the 4 projects and try to link with the presentations that we're going to be seeing today. So the first one would be Helios, which states for high performance modular battery packs for sustainable urban electromobility services. So this project is focusing on a hybrid combination of high energy cells and high power cells by means of a modular approach, making use of DC-DC converters. They will also be going to be working on advanced BMS systems, multi-sensory units, by using wireless communication, also working on digital twins, IoT, cloud-based technologies, focused on fleet management softwares or fleet management itself. As I told you before, ultra-fast charging, which is common to all the projects, if I'm not wrong, and they are going to be validating their developments in a small city electrical vehicle and a full-size electric bus. So that's little introduction to Helios. If we move to the second one, which is going to be MARBLE, well, MARBLE stands for Manufacturing and Assembly of Modular and Reusable Electrical Vehicle Batteries, a battery for environmental friendly lightweight mobility. Again, in this project, we can see like very common KPIs for us or for the call, which is 20% weight reduction, 25% charging time reduction, and in this case, 40% LCA improvement, together with the life cycle increase. And they have a strong focus on easy and safe disassembly, automatization, reparability, and second life. And they are meant to be adaptable to all the cells and vehicles, or those developments are meant to be adaptable. So in regard of these projects, today we are going to be focusing a little bit on a hybrid combination of high energy and high power cells. And we will have Juan Alberto Romero, IREC student, in collaboration with Vitesco, also Vitesco employee, if not wrong, with a presentation entitled Balanced Strategies for Batteries with Mixed Chemistries. So just a little bit of the developments they have been doing there. Hope you like it. In regards of MARBLE, we are going to be focusing on these last 2 points, which are easy and safe disassembly automatization, reparability, and second life. And we will have Lluís Trilla from IREC with a presentation entitled Modular and Connected BMS Technology. So thank you both, Juan Alberto and Luis, for being here, and hope that the audience is going to like your presentations. Last but not least, the other 2 projects in COLLABAT. So the third one would be Albatros. So Albatros stands for Advanced Lightweight Battery System Optimized for Fast Charging, Safety, and Second Life Applications. Again, we see common KPIs related to weight reduction, recharging time, and useful battery life enhancement, as well as LCA improvements. In this case, they have a strong focus on sensorization and thermal management knowledge, and they are going to be validating their developments on a BMW i3. Fourth project, which is going to be Liberty, that I am coordinator in this case. So Liberty stands for Lightweight Battery System for Extended Range at Improved Safety. And we are focusing or envisioning how to reach those goals with a cell-to-pack solution, with an immersion cooling system and enhanced safety system also, together with advanced BMS and SOX algorithms that will be validated in a Mercedes EQC electric vehicle. So in the case of Albatros, we are going to be focusing today in the useful battery life enhancement and sensorization, and we will have Hazal Sölek from FEV Türkye with a presentation entitled AI-based BMS models. And in the case of Liberty, we'll have a talk regarding advanced BMS systems, and we will have in here Radu Schwarz from Fraunhofer Institute, presenting flexible open source BMS adaptable to different use cases. So thank you again, Hazal and Radu, for being here. And I will introduce you to those presentations just in a moment. But before that, just a few more things about the COLLABAT cluster and about our structure and which are our objectives. So the cluster itself is divided in 4 subclusters. First one for sustainability, which would be subcluster A. Subcluster B would be about testing. Subcluster C, BMS, which is what drove us here. And subcluster D, which is going to be modeling, right? So our main goals are to engage on technical topics and technical discussions, to work on the synergy that we have. We already saw that the 4 projects come from the same call, so we have a lot of common topics that lead to synergies, right? We expect to provide specific valuable outcomes for upcoming new projects. That's one of our objectives. Of course, showcasing and dissemination events like the one we are here today, and generation of white papers, guidelines, journals, and that kind of materials. Just a last remark. So we are now launching, or this is the first webinar of a series of webinars related to BMS. The next one coming will be the testing webinar, the 26th. I have here the details and you can register. The next one coming will be sustainability, followed by modeling, which we still don't have the exact date defined, but it will come after the next two. So if you like what you are going to see today, please join them, and you will be more than welcome. Finally, I just leave here the contacts of each project, just in case you need or you want additional information. Please feel free to contact all of us, and we will do our best to answer your questions. And after this, time for me to give the floor to Radu Schwarz from Fraunhofer. So Radu, please, you can share your screen, and welcome to the webinar. Sorry. Okay. We cannot hear you, Radu.
Yeah, I'm just
okay,
starting. Yeah.
Okay,
Thanks.
perfect.
Good morning, everybody. As already introduced by Edu, I will give a short talk on our BMS activities at the Fraunhofer IISB. Fraunhofer IISB is located in Erlangen, southern Germany, and one of approximately 80 Fraunhofer institutes of the Fraunhofer Society. I will talk in special about the flexible open source BMS platform that we call FOX BMS. A short introduction on our activities. So I'm a group lead of the group battery systems at the Fraunhofer IISB, and we are designing and prototyping high voltage battery systems for special applications with, let's say, demanding requirements. We are pretty much focusing on mobile applications, and this can be either automotive and road transport, but in the last years also rail and transport sector grew in terms of electrification, and in the very last years also aviation and aerospace is booming in this sector. And what of all these battery systems have in common is the battery is still accounted at being dangerous and must be supervised or monitored by a BMS. So for sure, if we want to design and provide the complete battery system, we have to include BMS. And therefore, we are also working highly on these topics. Back in 2015, we started the project FOX BMS, which was meant back then to be a successor of our tricore-based BMS developments that became very complex and maybe too complex for a group at the research institute. So we decided back then in 2015 to initiate this project and to focus more on modularity, flexibility, and also on simplifying things. And the idea behind FOX BMS was also to provide this platform to customers to being easily adapted to their use cases. And so to enable different players in the supply chain to start developing their own BMS solutions. And this can be either the hardware, the software, algorithms, BMS behavior, or the complete package. And as you can see, we have quite a broad range of customers up to now, covering the complete supply chain of BMS development and manufacturing. So starting from the academia, which is often focusing on modeling or data acquisition, so doing just measurements with the BMS. Then we have a lot of customers coming from the tier 1, tier 2 suppliers. They were looking for an easy entry point to get started with the development of BMS solutions. And we have also customers coming from the, let's say, OEM side. They were looking for a platform that is flexible and easy configurable to enhance their series or research activities without relying on a very complex and very not easy adaptable series product BMS solution. Back in 2021, so 2 years ago, we started the second generation of Fox BMS based on the requirements we received and the discussions we had for several years with our customers. And I will go in detail on this Fox BMS Generation 2 on the next slides. The main difference, because you may be aware already of the Fox BMS platform, is the transition from 1 to 2, as we were focusing pretty much now on functional safety. We provided a lot of kits and had a lot of customers using Fox BMS Generation 1, and there always came the question up how to certify their product, how to go along with the certification of the BMS itself, and also the complete industrialization. And therefore, we saw that Generation 1 was pretty much focused on the open source idea, but not on the functional safety as it may be required for different applications. As our customers are coming from various domains and applications, we then first had to check for the main core of the BMS, the MCU itself, how to select it, which one to select, to comply with the various customers we have, and also their domain-specific requirements. And so we came up to one of the most flexible MCUs from Texas Instruments. This is an TMS 570 microcontroller, safety microcontroller that is capable of being certified not only for the automotive domain, but also in the aerospace aviation domain and also for the industrial applications. And as Fox BMS meant to be a development platform, we want to stay flexible, and we try to cover all these domains within one platform. And therefore, the selection of a flexible microcontroller unit was crucial for this project idea. So we are now targeting multi-applications, so automotive, aviation, industrial, rail, marine, maybe military applications. And we're now pretty much focusing on functional safety. So what we are currently still working on in Generation 2 is to enhance certification-ready modules in terms of the hardware and also the software parts. This means that we are developing according to the processes defined by the relevant norms and standards, so that these parts can be adapted or used or reused for specific applications. Fox BMS can be also be understood as an evaluation platform. So we are also relying on cutting edge components from several partners. Mainly, we try to have a good relationship to semiconductor manufacturers to use the latest and cutting edge components. Also, and I think I will not go that much into the detail, but because we have other presentations covering this topic, but Generation 2 is also enabling cloud connectivity and using of novel AI-based state estimators, and therefore we also enhance the interfaces of the BMS itself to be as modular and flexible as possible. The Fox BMS platform is meant to cover all the development supply tool chain and process from the philosophy or engineering requirements and going to the industrialization. Therefore, qualification of several parts in the BMS itself is mandatory. With Generation 2, we specially enhanced this capability. So we are developing certification-ready modules, as already mentioned, as well in the hardware, but also in the software. And just to give an example, the most highly functional safety rated functionality, such as voltage measurement, is rated up to ASIL-D in the automotive use case. In the aviation, it's called DEL-C. In the railway, it can be up to SIL-3. And in industrial applications, this can be SIL-2 or SIL-3. But with this FOX BMS 2, we now are providing solutions to enable this qualification at our customers. For sure, something must be optimized because it's a development platform, but we enable this activity, and we are also supporting our customers going towards the full industrialization of the BMS solution, and also the complete system that is sometimes provided by the customer itself. Now coming maybe to the license model, because this is for commercial applications and partners a very interesting point. We selected FOX BMS to have non-restrictive licenses, so that we fully enable commercial use of the complete system, but also only parts if needed. The software is licensed under a very open BSD license, and the documentation and the hardware is licensed under a Creative Commons license. I think the most important point here is to mention that we have selected to stay with no copyleft restrictions. That means that usage of parts or the complete FOX BMS solution within commercial uses applications does not enforce anybody to republish parts that were used from FOX BMS, but also we will have not to be mentioned, or anything must be reopened or republished under the same license as it was before. This enables our industrial partners to do whatever they want with the FOX BMS platform and parts within. Now I'm just coming to some more details, how the FOX BMS platform looks like. You can see the BMS master in special. So following very state-of-the-art architectures, we are providing a BMS master, which is the main control unit, talking to higher level control units in the application. So this can be a VCU in automotive, but can be also higher level energy management systems in stationary applications. The picture you see, or the board you can see now, is the BMS master unit we are providing to our customers, but also using in our own developments and projects, such as, for example, Liberty in this case here. The board itself is relying on the already mentioned TI-TMS safety MCU. We have an architecture selected with a dual system basis chip configuration, one supplying the MCU and the other one supplying the peripheral components. The main part is to be mounted on this interface to the analog front ends, which are placed on the battery modules, measuring cell voltage and cell temperature. And as we are following a modular approach, this can be interchangeable within this development kit for customer-specific or project-specific developments. We can embed this on a single board, but to be as flexible as possible, we can add here a specific BMS interface translating the SPI signals from the MCU to the very specific analog frontend or BMS slaves used in the specific use case. To provide also modularity in terms of the integration, we are providing several communication interface. We are currently relying pretty much on CAN. For stationary applications, also RS485 is supported. We have added the Ethernet support, which can be used also to stream out a lot of data to maybe edge devices and then forward this to any cloud services to enable AI-enhanced state estimation algorithms. We're providing a lot of connectors to drive contactors. And as you can see, we are supporting an extensive amount of contactors. This is meant to be as flexible as possible because, for example, we have seen or developed systems that are relying on multi-string or multi-pack approaches to enable also this use cases. We have added a lot of contactor controls here. To just give a short word on the software architecture. So we are relying on a real-time operating system, FreeRTOS, that can be also switched to a certifiable real-time operating system, SafeRTOS. And the architecture is as follows. So we have divided different functionality of the BMS and application into different tasks that are mainly driven by 1 millisecond, 10 milliseconds, and 100 milliseconds. And there is also a special task with a lower priority for algorithms, also within 100 milliseconds tick. The blue parts are optimized for simple customization, either by us or by the customer or within a bilateral project. This gives a lot of flexibility in terms of use cases and also technologies. A short overview on the configuration and modularity that we are providing. So the main part is relying on the already mentioned MCU. We can switch from an open source and available real-time operating system to a certifiable operating system. The interfaces and the API has been adapted to enable this switch. We have support for various measurement ICs, so analog front ends, that are currently supported in the free version. We have others that are available under NDA. We are providing different support for temperature sensors connected to the BMS slave. And for sure, the main part that has to be adapted to the specific use case and application is the system control, such as number of strings, modules, cells, contactors, to enable the BMS to be used within the specific use case according to the requirements. Now you may ask, I have the BMS hardware, how to start? Usually we provide the documentation and the software description on these links. Once you set up the BMS toolchain, you would easily be able to compile your code and deploy it. We have defined a very lean interface to interface with your custom models or algorithms. There is a few requirements coming from the toolchain itself, but also the hardware. But if you comply with these, you are pretty much flexible and can adapt the Fox BMS in terms of software and algorithms or system behavior to your likings and to your requirements. Finally, just to give a short overview on project examples. One is the recently finished EU project 1000 kilometer plus, where we designed a retrofitted battery system for Mercedes EQC. The intention was to reach a road approval with this vehicle, and therefore we had to comply with several regulations in terms also of a development process. Fox BMS 2 was used within the system to communicate with the vehicle. So we covering here automotive application use case, and pretty much in contrast, we supported, as an example, a student team from the University of Zurich in Switzerland. They have been electrifying a small four-seater electric airplane where we provided the BMS solution, so the BMS master, customer-specific BMS master, and also the BMS slaves that have been approved by the Swiss Aviation Authority, and they were able to fly with this plane with the Fox BMS inside. This was to give you a short overview on the flexibility and modularity of the platform. short acknowledgement. Parts of this work have been funded by the Liberty Project that I'm also representing here during this presentation. Thanks for your attention, and I'm open to questions later on or in the special chat. Thanks.
Thanks a lot, Radu. I think you already have a question there. We can dig about that a little bit more in the Q&A also. So thanks a lot. Very impressive platform, to be honest, and a really interesting presentation. I will save my questions for later on. And now I would like to welcome Lluís from IREC, Lluís Trilla, with a presentation titled Modular and Connected BMS Technology. So please, Lluís, when you are ready, you can share your screen.
Okay, I think I'm sharing. Hopefully you can see.
Yeah, we can see it.
Okay, excellent. Well, as mentioned, I'm going to present what is the approach for BMS development in the project Marvel. We are mostly focused on modular and connected technology. But let's see, first I will give a quick overview of the strategy that we are using. But first I would like to show you what is the issues that we want to tackle in this project related to the current BMS technology. Well, first, that BMS is typically wired, so that requires a lot of wiring hardware, a lot of physical connections internally in the battery pack. Then we identified that most BMS technology are centralized, so you depend on a central unit to manage the whole battery. They are typically offline. Of course, you can connect to it by physical connection, but they are not well connected or remotely controlled. It's not available. And important, they are tailored technology to a specific battery system. So what we proposed in the Marvel project is to develop a wireless BMS and removing all the cabling inside. Also a decentralized strategy to enable all the modularity. It also has to be cloud connected to have interaction with some external agents, and also to provide flexibility. Flexibility in the BMS design, but also in the battery pack design. So if we go step by step, what we proposing here is to have a wireless system, radio frequency based communication system, which goes from the cell that has attached a device that we call the Smart Cell Manager. It performs the balancing and also performs the measurement of temperature and voltage and transmits all this information to the module control unit, which is attached to each module. Then the modules can pre-process this data and send it to the battery control unit. Then, by a decentralized system, what we have is a system that can incorporate as many modules as we want inside the battery pack. We are providing a module control unit that can operate the module by itself. So we can go from single module operation up to several module units, and all of them are coordinated or orchestrated by the battery control unit. In Marvel project, what we are going to test is from single module operation up to batteries of 400 volts, and then moving to 800 volts with the same BMS technology, just to prove this decentralized approach that we are proposing. Then we are provided the cloud connected technology. This is happening through the battery control unit, the BCU, which has a cybersecurity layer to ensure that the communications are secure. It can exchange data with a control center, and from the control center we can provide some features like remote assistance, which is basically an artificial intelligence-based predictive failure algorithm This is done to increase or to ensure the safety of the battery system. And also we can provide some more accurate state of health and remaining useful life prediction. By itself, it's a powerful tool, but in particular, it's very interesting if this kind of technology is deployed to hundreds or thousands of battery systems, because then we can quickly generate some significant databases and we can identify if there's some misbehavior or some potential issues with some battery system that is not performing correctly. We can detect easily anomalies in this way. And then, of course, we have the flexible approach of the BMS, which comes from the software upgrades that can be provided from the cloud through this control center to the battery control unit. And there are three approaches that we are exploring here. One is to improve the performance of the battery system. That can be done by changing dynamically the operational limits of the battery, but also we can replace, let's say, the old controller in the battery control by a new one. This is in particular interesting when the battery is aging, and then we have to update all these estimation algorithms on the internal models that are at the VCU with some others that match better what is the actual dynamic behavior of the battery. But also we can replace what is all the algorithms in the battery control system when other chemistries, let's say an upgraded chemistry or maybe using a different manufacturer, is used with minimal changes in the BMS. It also allows us to change the communication protocols. Let's say the EV battery is it's programmed to communicate with the ECU, the control unit in the vehicle, through some specific communication protocol from its manufacturer. But if we are changing from one vehicle to other or from different manufacturers, we can update this communication protocol, but also it will enable second life because we can substitute this communication system by other that it's adapted to power inverters, for instance, if we are using the battery in second life for other applications which are stationary. Well, this is a quick overview of the technology that we are developing. And just to give a quick summary of what is the status of the Modular project, all the components of the battery pack and also the BMS are currently being manufactured as we speak. So we have run some partial in the laboratory preliminary tests, which have been successful, and they show that the system is working properly. The battery assembly itself is planned for the first quarter of next year, and we will have the first test results available in the second quarter. So hopefully for the next webinar that we are planning to have here, we will be able to show some results to all of you. And well, that's all from my side. We can have some questions by the end of the session. Eduardo, it's all yours.
Yeah, thanks a lot, Lluís. Again, very interesting topic. I think I have quite some questions, and probably audience does the same. I will save it for the end. Thank you again for that presentation. So now I would like to give the floor for the next presentation, which is going to be balancing strategies for batteries with mixed chemistries by Juan Alberto Romero. So please, the floor is yours, and thank you.
Thank you very much. Just tell me, please, whether you can see my screen.
Yes, we can see it.
Okay, perfect. So thank you very much. Welcome today to this small overview about the balancing strategies that we are following for the Helios project within this COLLABAT collaboration. So very short from myself, I'm Alberto Romero, research engineer through the PhD program by IREC, as well as I'm a full-time employee at the Vitesco Technologies company here in Germany. Regards of the balancing strategies, we have here a very short overview. It's very difficult to pack in only one slide all what it's all around battery balancing. There are several applications, several approaches over the time being. So the very classic one is the such called passive balancing with a switchable resistor across the battery cell but even the battery module. The main target of it is only to compensate the different agings that the cells are having over the lifetime. And you will find here balancing currents around about 100 to 200, 300 milliampere maximum, as the heat generation here across could create a temporary hotspot across the battery cell or around the battery cell, and this additional heat generation is not target to have in this application. Also, the tolerances of the cells produced are getting even slightly, so it means that the cell balancing topology is a lot of times even not used. It all is compensating, as I said, this very small aging that the cells are having over the lifetime. When we are going towards different approaches where either you can spread a little bit of production out of the cells, we have seen over the last 20, 25 years already, even 30, different approach of active balancing topologies. So we have either typical capacitor switch, either with one level or two levels, which we are transferring the energy as kind of efficiently from one cell to the other in order to compensate the different capacities that the cell are having during the real operation. Or we can follow also inductor-based approaches, which are only also transferring energy from one cell to the other, either with only one inductor located into the module or the pack, or with several inductors. These have their own constraints, as the energy which going from, for example, from the upper cell might go through a lot of cells until they reach the most aged cell. So the tolerance or the energy sharing across the different concepts is sometimes very difficult to achieve. Other approaches are typically using a galvanic insulation transformer, either to push up the energy out or push down the energy out of the cell to the whole string or the module, either in one direction or both directions. So literature is very extensive at this stage. You can find a lot of several approaches. What it's winning over the last months, years, a little bit more interest is to what we call power balancing. So the main difference between the active and power balancing is that their semiconductors are having the full current of the power path that the cell is seeing. So if you can imagine here, all the circuitries are aside of the main power path of the cell. Here, the circuitry is seeing the power path of the cell when it's enabled. It also brings additional flexibility, because depending on the circuitry, you can even blend out smoothly, intelligently the cell out of the power path. So at the end, depending on the approach we are following, we can find an improvement of the capacity utilization depending on the operating temperature around about 4%. With introduction of this active and power balancing strategies, but this benefit achieved should always compensate first, and the most important thing, the cost of the introduction of this technology. Secondly, introducing more electronics increase the risk of reliability issues at the module level. And you can imagine whenever you want to achieve balancing at cell level, you have to add additional switch a lot of electronics at the battery pack, which increase the risk of having a single or multi-point failures. We from Helios have followed two decisions within this project. First, we decided to introduce the battery chemistry differences, as we are introducing different chemistries in this battery modules at module level. It means we build up modules of only one single chemistry, and we pack them all together to achieve our target application. So this concept is fully scalable and fully modular. So depending on the real application we need, we can pack different amount of power modules in series and back it up with a DC-DC converter with additional battery cell module. And these chemistries might be different. Here's an example. We can see that the traction net side would be linked through high power modules based on LTO chemistries, and they are, the half of the pack is backed up through a DC-DC converter with a configuration of 2 parallel modules of high energy cell chemistries, means typical NMCs we can find out of the market. As we are working in Helios with, let me say, commercial cells, we identified at the end not the benefit of introducing active balancing at module level. Therefore, we stay with passive balancing at module level, but we do increase a little bit the current of this passive balancing to enhance the availability of the battery pack. So we want to try to balance a little bit faster than the typical use case, around about 100 to 300 milliampere. So we are going beyond that. We will generate additional heat, but we introduce a smooth thermal management concept to get this thing cooled down and capable to be driven. All these modules will be connected at the set with this DC-DC converter, which is taking the energy share across the traction net and what's being backupped through the range extenders cells or high energy cells. We can imagine to have several of them parallelly connected with additional DC-DC. So additional perspective of this scalability can be achieved with that. Finally, also worth to mention that we are fully communicating wirelessly. Each of the modules is communicating with a central BMC microcontroller. And all these modules, either if it's high power, high energy, are looking like exactly the same from the outside. So they are mechanically, from as a black box, identically the same. They have the same interfaces, the same electronics on it, and they are freely scalable to be driven. That's all. This was a very short overview. I also paid attention a little bit on the clock for not hijack the series, Eduardo. So you can find here my both addresses from the corporative as well from IREC. And this project is also, of course, founded by Helios. And therefore, here they always reference the grant agreement. So thank you so much. I'm looking after for the questions.
Thank you, Alberto. Appreciate it to be timely. I have quite some questions. You are completely right. Like 10 minutes is not that much, but really interesting. We'll try to dig a little bit deeper in the Q&A and in the panel. So thanks a lot.
Thank you.
So then last but not least, I will give the floor to Hazal from FEV Türkye for the presentation entitled AI-based BMS models. So please, Hazal, the floor is yours. Deserving to see your presentation.
Hello, everyone. Just a sec, please inform me when you see my screen.
So we are seeing you, but not the screen.
Still, can't you see?
Seems there you go. Now we
Okay.
can see the presentation.
Okay. So I am Hazal Sölek from FEV Türkye, and I have been working as a technical specialist in battery system departments for almost 4 years. In this project, I am responsible of BMS software development in the Albatros project. Before beginning, I briefly want to introduce FEV. We are a worldwide engineering service provider, and we have more than 7,000 employees all around the world. And we able to support our clients with our test centers and professional engineering team from concept phase to series productions. Battery system is our one of the major scopes, and we can support projects from cell selections to series project productions, includes vehicle test calibration and hardware and software designs of the BMS systems. In Albatros project, at the beginning of the interest of the meetings, the projects already introduced, but what we are doing in Albatros projects, we are responsible of the hardware and software development in Albatros projects, and most of our algorithms is in patent application process now. And today I will explain our AI-based algorithms in this part. Before starting, I want to show briefly the software architecture to create a clear vision of our software, because today we already focus on the AI-based parts of the algorithms. But in left-hand side, you can see the picture of the graphics of our software architects. And we have a online electrochemical impedance spectroscopy in our vehicles. And according to this board, we are calculating battery parameters in Thevenin equivalent circuit parameters, as you know, series resistance and capacitance and polarization resistance in these models. And we are calculating these parameters according to electrochemical impedance spectroscopy. And with using these parameters and online measurements as voltage, current, and temperature measurements, we are running our software algorithms in shows in the right hand side of the presentations. You can see the base main approach in these algorithms that use in our software. Today we will focus on the SOC, SOH, predictive thermal management algorithms, and anode control charge parts, because these are based on the AI models. First of all, I will explain the SOC estimation algorithms. And as you know, there's two main approach in BMS algorithms that used in current BMS boards. First approach is model-based algorithms that commonly used part is this one, but accuracy of these models highly depends on the model that you developed, and because of the nonlinear characteristic of the battery, it's not easy to model all battery characteristic with a model. That's why AI-based systems are started to use in BMS systems. These AI-based systems are basically data-driven methods that use the input data to determine the battery states and battery parameters. These AI models most likely a black box system. Just you are putting some input data and training according to this data, the system, and you are getting some outputs from these systems. These AI systems accuracy is most depending on the training data and the test that you get these training data. So we commonly use the LSTM, long short-term memory neural network systems for our AI-based algorithms. Why we choose this LSTM or long short-term memory neural network systems? It's basically because of the high accuracy of these neural network systems. It's because of the this system has a feedback mechanism, internal feedback mechanism, and a memory effect. So we can easily shows the short and long-term data to estimate our outputs. And that's why we choose this LSTM methodology. For SOC calculation, we are using a hybrid method actually. We combined both model-based approach and AI-based approach because both of them has different positive sides. That's why we combined them. With state equations, we are using the Kalman filters to filter the measurement noise. And with AI part, we are predicting the SOC, and using this Kalman filter, we are filtering the SOC outputs of the AI-based algorithms, and we put a final SOC value to output of this system. How this system works? First of all, we are using the electrochemical impedance spectroscopy to determine initial RC parameters of the equivalent circuit models, and this systems work when the vehicle is in park state. So we are assigning initial parameters here, and we feed least square algorithms to these values to put initial values of this parameter of the battery. And in online part, we are running the least square algorithms to specify the parameters, and then we are using the Kalman filter to estimate the capacity of the battery. And also we have online measurements here, the voltage, current, and temperature. By using this SOC capacity and the measurements values, and also previous SOC value, we are running this hybrid methodology, and we are getting the SOC value as the output of this system. Second part is SOH estimation system. For SOH, we are using a cloud-based AI for this part. Actually, we are, as you know, SOH is change rate is slow than the other parameters. That's why we are running our algorithms in cloud with the data storage of the vehicle, and sending this data to cloud, and calculating our SOH value and send back to vehicle. So it's always, as I mentioned, we are all using the LSTM methodology here. And the other part is thermal management. In as a difference from the previous, we are using a different approach here, because we are using AI systems to predict future temperature of the system. We are getting surface temperature, coolant temperature, and voltage and current values from the cell, and we are using a algorithm to predict the internal temperature of the cell, and we are using the internal temperature value to feed our AI algorithms to predict the future inner temperature. Why we are using this path? Because we want to predict the, for example, the fast charge temperature in future, and that's why we can optimize the charge time estimation algorithms, also the current values in our charge process. The last one is anode control charge. As you know, the fast charge is one of the trend application in electric vehicles. During fast charge, we are applying a high C rates, and it's occurs the lithium platings in battery systems. That's why it affects the durability and safety of the battery packs. That's why we are using the anode control fast charge algorithm to prevent lithium plating. Basically, you cannot directly measures the anode potential in battery. That's why we are using a AI-based system to predict anode voltage of the cell. And using this anode voltage, we are feeding a PID controller to set a charging current. And according to this charging current, we are sending this value to charger, and we are getting back some of the voltage and current values from our cells, and we are training as offline one more time our AI systems. These are the main systems that we used, AI systems. Thank you for your attention.
Okay, thank you, Hazal, for the presentation. Again, very interesting, pretty different topic from the previous ones. So thanks a lot for that. So now that we have seen all your presentations, we already have some questions in the chat. I will try to do a mix up or just leave it for the Q&A section. So thank you for the people posting your questions in the Q&A. We will address them just for you to know that we already saw them. So now I would like to open the panel discussion. That's going to be roughly half an hour before opening the Q&A. And I would just like to go first to some specific questions about the presentation we just saw, together with some more general questions that arose during the subcluster meetings that are more general to BMS systems, let's say. So first of all, about the Fox BMS platform, well, actually very, very interesting. You already mentioned something, but could you give us a bit more detail about or which are the main differences between version 1 and version 2 of the platform? You already mentioned that the MCU is changed due to certification or pre-certification topics, but I don't know if there is any other significant or meaningful difference, or what were the main challenges that you were facing in that process of migrating. I guess that migrating a platform like such it's quite a challenge.
Yeah, sure. So first, generation 1 was also meant to be a marketing platform. Therefore, the focus was on availability of parts, and we selected very popular components like the STM32 microcontrollers that are widely available, and also, for example, as we are also relying a lot on student workers, this is a well-known platform. For the generation 2, we focused on functional safety. So as also, I think there was already a question on that, we had to overthink or rethink our system architecture, and relying on industrial grade microcontrollers gave us some problems in terms of certification. And a lot of things required by functional safety cannot be implemented with such type of architectures, and a lot of additional software work had to be done in Fox BMS 1. And this is again a pain for certification. Therefore, we switched completely to another architecture, relying on a safety MCU, which does a lot of functional safety relevant checks already in hardware and must not be taken into account in the software. This is one of the main changes. The challenge was to get in touch and get these things running, because these are much more complex also in terms of debugging these type of microcontrollers. But as the software architecture was already modular, we were able to transfer the application layer of the BMS itself also to the generation 2. But for sure, the underlying low-level hardware drivers must be rewritten for this type of transition.
Yeah, sounds challenging indeed. So okay, that's very fair answer. So you changed the full structure of the BMS together with some parts in order to be safety oriented, let's say like that.
Correct.
Interesting. Just a couple of more questions, not that we are with this topic. So in regards of algorithms deployment into the BMS, I mean, we have a real-time operating system in there. We have quite a complex software embedded in the system. So you just mentioned that, and there was also a question in the chat or in the Q&A regarding algorithms. You have a basic set of algorithms in the BMS available, and you just answered that, of course, cell data is not available at this stage, and you after that can generate ad hoc algorithms or advanced algorithms, let's say. So I would like to ask, I mean, is there a specific challenge when we are going to, or if one would like to implement advanced algorithms in this Fox platform, or there is something that we should be taking into account in terms of probably memory? I saw you also have an external memory interface in order to probably get more flexible. I don't know, just some hints about that next step.
So the biggest challenge is to separate safety-related functions from these non-safety-related functions. And during the certification process or development process and testing, you have to ensure that these are not interfering with each other, so that, let's say, memory or computing time heavy algorithms will not affect the functional safety relevant functions. I think this is one of the biggest challenge. Depending on the state estimation algorithms, maybe we have to, or you have to adapt on the task structure within the operating system. So you have to keep in mind that there is already some underlying basic functionality that must also still keep some memory and get some computation time on the MCU. But as long as this is ensured, you can add also non-safety related AI-based functionality to that. To make things more easy, we have an memory interface where you, for example, can add also an SD-RAM. We had this also on Fox BMS 1, where you can add, let's say, bigger arrays or matrix that is needed for AI-driven approaches.
Okay, thanks a lot, quite clarifying. Don't have much more questions. I will leave for the Q&A. Are you planning a third version or still busy with the second one?
I think we are still keeping with that. There is already some improvement ongoing or planned, but we will not name it Generation 3. Okay. I think this is meant to be, if it's a major redesign.
Still quite young platform, the second version.
Yeah.
Congratulations for that. Okay, so thanks a lot, Radu. Again, very interesting. I would like to move to the Marvel presentation. Again, we shift a little bit from topic. Lluís, you have been talking about modular structures, wireless connectivity of batteries or BMS slaves, I would say. And so I do believe that unlocks a lot a full potential of a BMS, I guess, in terms of production, assembly, in general robustness of the system, that we are not error prone in terms of cabling, connection, and so on. I don't know, how do you see that this impacts in the actual development of a BMS, and related to that, would you say that it's something that it's easily transferable to a second life scenario in which we could reuse those slaves, or it's something let's say, more closed and remains in first life?
Okay, maybe to answer your question, well, step by step. The first approach of
Probably
using
too long question.
No, it's all right. No, so the idea behind using wireless communication, it's it's targeting one of the objectives of the project to reduce weight. So we decided to remove all the cabling, so there are only power paths inside of the battery pack. And additionally, we wanted to enable the automation of assembly and disassembly of the battery. So this is targeting to drop down costs and to enable the mass production of the battery systems. And then, of course, since we are developing this system with this modularity that I was explaining, we wanted to facilitate the transition to second life. And by using this kind of system, of course, as I mentioned, we can develop a 400-volt battery system or 800-volt, but we can go bigger. So for second life application, in particular to grid-connected stationary batteries, which can have hundreds of modules if necessary, we wanted to target this possibility of putting together all the modules or even the battery packs, full battery packs, and let them interact to each other with this connectivity that we are providing, and to facilitate this removal, refurbishing process with removing all the cabling inside.
Okay, sounds, yeah, I mean, that's actually very true. You can extend the voltage of the battery quite a lot easily, and that's a very good point. And honestly, didn't thought about the weight of the cabling. That's also a very good point. Really interesting. Just maybe in the other side, do you see any challenges? I mean, is this implementation, let's say, somehow straightforward? We have IC solutions for the task. What state of maturity are you envisioning there?
Okay, for radio frequency-based communications, yes, there are some commercial solutions that you can find. Some Wi-Fi based or Bluetooth based, they are already available. But of course, there are some challenges here. We are studying two of them. The first one is, of course, what is the role of electromagnetic interference? Well, we know that batteries are coupled to a power electronic system that can emit quite a lot of radiation. So we have to keep an eye on what the interferences can be, how they can affect communications, and this is something that we are going to explore in the second part of the project. And of course, there's the risk of cybersecurity threats. In current technology, you have to connect physically to the battery, let's say, so that it's a barrier that it's removed when you are using wireless communications. We have to make sure that somebody externally to the battery system cannot access to the data or modify the software somehow. So we have put some intermediate layers to protect the data exchange in the form of encryption of the data, but also securing the access to this data with some credential manager.
Okay. Really nice answer. I mean, you already smashed my next two questions, and cybersecurity is, of course, crucial, and electromagnetic interferences. I think that's one of the key points that for the ones that we are coming from the electronics pop out when we are talking about these systems, and completely worth. I mean, good thing to hear that you are putting an effort in terms of Marvel on that. So I definitely will keep an eye on it and hopefully see some more results. Just one more short question, and I don't know if you are going to be able, or you have some vision about, but do you see any challenge in terms of data transfer rate between the slaves to your master unit, or it's something not so meaningful, especially if we are increasing the number of battery modules or increasing the voltage in which we are going to serialize more batteries. Is that something that the Wi-Fi or wireless connection is going to help, or is going to be more like a bottleneck?
Yes, that is right, that it can be a bottleneck for data exchange. And this is why in this decentralized solution, what we are doing is transferring most of the computation to the model control unit. So we don't have to share a lot of data with the central controller, let's say the battery control unit. But as I mentioned briefly during the presentation, what we are doing is to pre-process the data and just to exchange with the central control, but also with the cloud, and some specific, the most meaningful information in the most, let's say, compressed way. So in this way, what we are working on that, but what we are trying to do is to reduce as much as possible the data exchange needs without reducing the capacity to provide advanced features. So this is some topic, a field of study for us, and we are working on it.
Mm-hmm. Okay, interesting. I just asked because pretty much, let's say, a key point when we are cabling. So just wanted to see the two different approaches. You had some highlights. Okay. Thanks a lot. Very, very interesting inputs. Thanks a lot, Lluís.
Thanks, Eduardo.
I would move a little bit for next presentation. I mean, I would like to be here asking for much more time, but we need to advance. So from the Helios project, Alberto, you have been talking about balancing systems, quite a trendy topic, I would say. And when we're at that point, I'm going to be a little bit mean, and I would pop out one of the questions that I more often hear about this, and it's what are the main benefits compared to the cost of this system? I mean, can we balance that equilibrium? Because you just mentioned briefly. What are your thoughts about that?
Well, this is the golden egg out of the nest, let's say. The problem is that there is no one solution fits all. Okay, so it depends very strongly about the tolerance of the cell production, the quality of the cells you are using in your real application. There are several markets and several producers of cells and several tolerances on the production line. And at the end, the aging is being affected about the quality of the production. Okay. Of course, there is always for a specific application a sweet spot about the quality or the money you put, let's say, on the production of your cell versus the money you could put into the electronics you add into your system in order to extend the capacity utilization. This should be always very carefully analyzed because, as I said, passive balancing, it's a still most used solution into the market. It's very robust as it is very simple, very reliable, and the end introduction of a new technology into the mass market or into real application is strongly dependent of this cost versus performance, or sometimes through the legislation. Mm-hmm. So whenever there is any standards or norms or any kind of upcoming legislation towards battery efficiency, the compromise and the weighting of this cost function of cost versus performance will be artificially being modified, yeah, let's say. So it should be always carefully analyzed. So what kind of chemistry do I use for my real application? What kind of approach is most suitable for the application I need? And how much money does it cost versus the effort of the development? because also is reliability and robustness, also what our colleague from Fraunhofer said, ASIL class or safety class is mandatory in any of the application. So compared when I speak about automotive world, in the past, we had only unintended acceleration on the combustion engine wall, let's say, as a safety goal. And here we have several of them around the battery pack. So the safety is never to be neglected, please. Okay.
For sure, for sure. Yeah, completely agree. It's really, for me, it's really interesting that the point you just highlighted. We have a new batteries regulation that it's pushing us for more efficient batteries, and in that sense, that's interesting. That's something that we still have to keep an eye on, definitely. And so in that sense, you are envisioning the benefits of this kind of balancings, like from the energy point of view, or it's more something operational in order to have a more balanced battery in terms that it's going to be easier to operate?
So at the end, the customer, what does see is the range.
The range. Okay.
So,
energy
okay, so capacity utilization means I do get more range out of the cells I do have. If you can get always a little bit more range, final range out of the cells, is what the customer will see. And is what the customer pays for. They do not care at the end how fancy your electronics are inside the pack. They do care that they go from A to B with the amount of kilometers they do have shown in their panel on the vehicle. As an automotive market application, of course, stationary does have other requirements, other needs. I'm very strongly focused in the automotive, of course.
Yeah, very, very clear answer. Thanks for that.
Sorry.
It's always good to have that kind of inputs from people that it's so close to automotive. I mean, that's really appreciated. And so a final question in this regard, is there any consideration in terms of different battery chemistries? I mean, is there any big difference between using different cells, or it's just more about the model? Is there any cell that gives, or it's more benefit, or has more benefit from this kind of systems, or it's just something, would say, transversal to all type of cells?
Well, it depends also on the depending algorithms. It's not only about the balancing by itself, but it's about the precision or accuracy, most accuracy of your SOC and SOH. So there are some chemistries which have a lot of challenges to get a nice accuracy in terms of state of charge. Whenever you speak about LFP chemistries, which is very long, flat curve, for example, you need to invest a lot in order to get this state of charge in a nice way. We see that we are introducing cloud in order to improve the computational effort and get better performance on the SoC, because they do all these effects are manipulating or affecting the other actuators algorithm. So you're getting a better performance of balancing whenever you get better results of the SoC, and at the same time you get better results out of your measurement chain. So it's, let's say, balancing is at the end of this effect chain, and the performance is strongly dependent of the other inputs.
Yeah, interesting. I mean, we tend to think about balancing, estimation, and in separate ways, but it's completely true.
Yeah, at the end, it doesn't matter what kind of balancing whenever you have an SoC algorithm which is providing higher than 2% of accuracy. What you win through the electronics, are you losing it through the wrong control of the electronics? Yeah. And also, last to mention, the electronics are not efficiency perfect. So they have like 90% plus. You're always losing a little bit of energy. So that is also a grade you have to consider by your cost function.
Okay. Thanks a lot for the answer.
Welcome.
So that drives me and allows me to make the jump for the last presentation, which was actually about state estimators from Hazal. Just few questions here. again, we are shifting the topic, but also very, very interesting. So you presented a hybrid estimation between, let's say, Kalman filter approach. I think it was a UKF Kalman filter and A-based model for state of charge estimation. So could you give us a bit more of an idea on what are the main benefits of that hybrid combination? I mean, it looks like a very interesting approach. Just wanted to highlight like what is what gives you.
Okay. As I mentioned at the beginning of the presentation, both model-based and the AI-based application has different benefits. For example, the Kalman-based is a state-based approach, and we have a feedback mechanism in this part. And also, because of the nature of the Kalman filter, it's affects measurement noise. So you can delete the measurement noise with using the Kalman filter, and you can improve the AI-based systems output. Also, what is the main benefits of the AI-based system? We don't have to model all nonlinear characteristics by using the AI-based system, because if you had any mistake doing the model-based approach in this type of systems, it will affect the accuracy of your outputs. That's why we preferred to use the AI-based approach to create a black box system for the battery, and we are improving our AI-based systems outputs by using Kalman filter. Actually, this is the main motivation why we are using hybrid systems.
Cool. Sounds really nice that you can take both benefits from the two different approaches. That sounds really nice. Another question about, I mean, just really short one about the anode control charge you just mentioned. Could you tell us a little bit more about it? I mean, whenever I think about this kind of predictions, what I do immediately think is about the sourcing of the data to generate those models, to train those models, and how to validate them. And that's quite impressive that you are using that kind of algorithm. So could you tell us a little bit more?
Actually, we performed lots of laboratory tests during our cells, and we get in this test we use the limits of the battery. So by using also the manufacturer's data sets, we combined both our test data and the manufacturer data. Together we test our batteries, and using these types also we developed electrochemical cell models that works as offline. So we validate these electrochemical cell models by using these two inputs: test data and the manufacturer's inputs. So the output of this electrochemical cell model is the anode potential of the cell. So we use this input to feed our AI-based algorithms. So both combining of them, we validate our algorithms as a cell-based. So the pack level validation is didn't started yet. We are waiting for the vehicle for this part, but cell level validations is done now.
Very interesting. I will keep an eye on that. Thanks a lot for your answers and for the presentation, of course. So I could say that we covered most of the topics in here. So looking at the time that it is now, I would like to now give the floor to the audience in here. So you have any questions? I mean, I have seen that you have been already popping some questions, and that most of them, actually there's one that is still open, have been answered, and so we can take a look at them and probably comment it a little bit more deeper, and and otherwise, if you have questions, please, now it's the best moment for it, and we will have our experts here trying to answer in them. So I will just directly read one from Emil Namor, and that is still open. So this one is directed to you, Hazal, and I would directly read. So could you kindly provide a few details about the
Yes, I need to check this part because I'm not the hardware expert of this project. I need to check with my friends and give feedback to Emil.
Okay, perfect. So thanks for that. Yes, so we'll try to give some additional inputs offline, let's say. Other than that, there was a question here from Xavier Arrastoa, and Radu already answered. And they were talking about having an MCU with a double core, or for safety purposes, or having two separate MCUs, and the task of double checking that. I know, Radu, if you have some more inputs apart from that, I mean, or probably explain a little bit more in detail what we were referring to.
Yeah, so I just wanted to highlight that a safety MCU has two cores, but they are performing the same. So you're just writing one core, you cannot access the different cores. So these cores are performing the same calculations. And as it is called a lockstep MCU, these are shifted in time, and there is a compare unit doing the plausibility checks between these two cores. So therefore you can internally ensure, the MCU does internally ensure that everything is working fine. And in case it detects some malfunctions between these, or differences between these two cores, it will report to the system basis chip, and this one is then able to reset the MCU. This is a complex mechanism to ensure that your hardware is still functioning as intended. If you have two independent single core MCUs, you have to take care of this by yourself. So for example, ASIL-D will require that you have some redundancy, but not only performing all this calculations double, you have to make or implement a decision unit. So how to deal with not plausible results between these two cores. And this is again software that has to be implemented and verified, and you have to verify for your certification process that this a decision unit is working as intended. And this gives additional complexity, and I think a short calculation. So I'm not aware of high amount prices, but for the current MCU of the Fox BMS2, I think we are paying around 50 euros, and for the Fox BMS1, it was almost 20 for one. So it's
At
the end, it does not pay off. It gives a lot of complexity you have to handle, and software is hard to certify. So wherever you can replace hardware solutions, software solutions by hardware solutions, these are easy certifiable.
Mm-hmm. Yeah, also the certification needs to be taken in that sense. For sure, software certification gets complex. You're completely right. Okay, thanks a lot. I just will go through this also quite interesting topic. I think that could, to some point, touch any of the speakers today. So here they are Jorge Pinto is asking about, in the Marvel wireless BMS project, which BMS roles are running locally and which ones are cloud dependent, and how to mitigate issues related to cybersecurity. And I say that all of you because more or less every project has a point in cloud-based systems. Something running locally. In the Liberty project, for example, we have that Fox BMS, and after that there's another layer with an edge device. So what do you guys see about local implementation and cloud implementation? Where should be that line defined? I know it's a a question with probably no answer, but knowing your thoughts in that sense could be valuable.
Eduardo, this is Lluís from Marvel. Well, I already answered the question, but I don't know if from the other projects you want to bring your view. Maybe we have a different approach here, and we can share our experience.
Yeah, sure. So I would go in terms of Liberty project. What we are doing is we have the Fox BMS platform as the BMS master, and after that we are communicating to an edge device, and that edge device is running some algorithms and AI-based algorithms that are after communicating to the cloud. In our particular case, we did it like that. Options again could be probably to execute the full algorithms in the cloud, but again, if you have not such a strong connection, could pose a challenge, and it is not clear still where is the limit. From my personal point of view, I would say that we still need to have some basic algorithms state of charge for sure in locally, and after that we can have different architectures in which we can continuously evolve and improve the algorithms. But I don't know if that's a common view that we all share, or it's just my particular view.
Maybe I can add something out of the Elias project. So in the Elias project, we do compute locally in the BMS still the state of charge and the state of health. We provide through an IoT device bridge, which is typically communicating with the BMS through CAN, and we're pushing data into the cloud where a parallel digital twin of the battery pack will be computed. So it will be updated parallelly, the state of charge, state of health, and also being computed remaining useful lifetime. The approach, we're still clarifying how to play back the data out of the digital twin towards the battery pack. So most probably we will update some of the parameters of the state of health algorithm during the running time, or every end of charging session whatsoever. We need to look at the details, but it's a pretty similar approach what Lluís and you, Eduardo, mentioned. At the end, it's strongly dependent how much calculation effort you have in the local vehicle or the local application. We are restricted to the method resources available.
Personally, again, I mean, some other thoughts that we already had internally is that, and quite in the line with what Radu said, the simpler you keep your BMS, it's more easier to make it safe. I mean, in terms of safety, to certify it. So again, something to have in mind if we are going to advanced algorithms. We can make many changes, but safety is always going to be there, and something to be taking into account really, really carefully, for sure. Okay, and something, I mean, just some other topics I had here that are coming from our intern. Yeah, Radu, maybe you wanted to say something.
I just maybe to add to this discussion, I would be interested in this wireless solution, because usually adding this wireless connectivity again adds up to complexity from our experience, because you would use a local MCU as a, let's say, bridge between the analog front end and your wireless bridge. And here the discussion again starts. Okay, now I have a MCU on a module level. What can I do there? How does this affect the overall safety concept? So I would be highly interested in maybe some more details from this perspective, but up to the partners.
So maybe I can start. So the front end at the module level usually does not incorporate directly the wireless transceiver. There's always an additional IC which is located at the module level. So you're having more intelligence at the end because you're putting a small microcontroller there. And besides the safety algorithms or the checksum and the communication protocol to create this network towards the central controller or the hierarchical controller, you have still a little bit of computational resources there you could use either to drive additional inputs or outputs of your local microcontroller and to compute perhaps a small version of any of the algorithms to prompt less data at the end to the cloud, or to provide a second path of data to the cloud. The wireless protocol by itself should be implicitly safe. If not, you should consider already, like also some ICs producers are considering, to have a second network parallelly, to have a second antenna working parallel. And so it depends on the IC approach, how they are ensuring the ACLC from D at this stage for the transmission of the data. And whether you can pack also some local computed value through the network as a kind of backup information that can make your diagnostic function in the central controller. There are not so many wireless solutions on the market, so they are from the biggest players. There are very few of them, and yeah, all of them have a unique selling point, let me say. Kind of slightly different.
Okay, thanks for your comment.
Yeah.
Lluís was also pointing at that kind of distributed data processing. They are also processing, if I'm not mistaken, something at not MCU level, but the next level. That's also quite interesting, really. The fact that we can go generating aggregated data in terms to go higher levels. Yeah, interesting.
Yes.
Okay. Okay, so I don't know, guys, if you have any other input to that topic. Just double checking the questions I have here, probably related to this. Something that pop out quite a lot, it's the over-the-air updates, firmware updates on the BMSs. Quite a new topic. Well, I don't know if new is the word, but quite a trendy topic in BMS, to have the capability of updating firmware, or not only that, updating parameters of the BMS. Here, cybersecurity gets a lot into play. I guess also that those wireless communications could affect quite a lot. I don't know if that's something that is just straightforward or not. And I don't know to what extent do you see that it's that over-the-air update technology is something already accomplished, or we still have some challenges in there. Just mention it because it's something that pops quite a lot in our internal discussions.
So yeah, we are thinking of these features. We are currently implementing that as a part of a CAN bootloader, but this is pretty modular, so we can implement this also through other interfaces as long as there is the bootloader functionality. I think that the most critical point is not safety, but security related to these safety topics, because there's different approaches. You can either reflash the complete firmware, or you can just update parameters of a model, so just values. But now you have to decide if this is safety related or non-safety related function. So I think updating just some parameters of an SOH algorithm will not have any harm or effect on safety functionality. But if you're going to start changing parameters, for example, voltage thresholds, affecting the operation, you will add up updating safety-related functionality, and this gets complex. So currently what we have implemented within Liberty is that we can deploy from the cloud service down to the edge device. But this is then non-safety related functionality like SOH. But we have also implemented more downwards direction, so from the edge device to the BMS master. But here we have to decide what has to be updated and will not affect any certification.
Mm-hmm. Yeah, completely true. Okay. Any other inputs to the topic? Any other experiences in this regard from the rest of the projects, or maybe just not tackling that?
It's always curious that the reprogramming or the update of parameters in a ECU is QM based, but the cybersecurity does apply. But as also Radu mentioned, only updated QM functionalities over real time do not manipulate functional critical classified parameters in ASIL class. It's not a good idea.
Not recommended. Okay, yeah, completely true. Okay, so just checking if there are no other questions from the audience. I would propose to close the webinar here. Just give me a second. Sorry, just trying to share my screen again with you all. Sorry for that. I know you are seeing my screen. No. Well, just we'll send you out the information, not really that meaningful that I shared right now. But I just wanted to remember you that this is the first webinar of a series of them. Please try to, or please not, or if you liked it, and if you feel like appealing to it, feel free to join the next ones. Thanks a lot for the speakers for being here, for taking the time to prepare the webinar and the presentations. Thank you for such interesting discussions. And again, thank you to the audience for being there, taking your time, popping out some very interesting questions. Hope you liked it. Hope it was useful and